In this video, I discuss some questions from Chapter 7 that address the most important topics, those being effective nuclear charge, the size of various atoms and ions, determining the electron configuration of ions, ionization energy, and electron affinity. When I'm thinking effective nuclear charge, it's important because many of the properties depend on the electron configuration and how strongly the outer electrons are attracted to the nucleus. We have attractions between protons and electrons, and then also repulsions between protons and protons, electrons and electrons. The ones that are relevant here is that the net attraction for an electron, what it experiences, is smaller when there are other electrons present than if they were absent. So we're considering what is the effective charge that that electron experiences based on the number of protons, and then accounting for the electrons that are shielding it. In our expression Z effective equals Z minus S, the positive charge, Z, that's the number of protons. You can look to the periodic table for that. And when we're calculating S for the shielding, we're going to count core electrons, those that have a smaller N value than the electron that we're analyzing. Effective nuclear charge for a 1s electron just goes up, up, up as you have more and more protons. But for a valence electron, we see that it reaches a maximum and then it resets. It goes back to a smaller value and then increases once again. So that is representing a periodic trend. That's what's being shown here left to right as I move across within the periodic table. The number of core electrons isn't changing. The number of protons is increasing, so the effective nuclear charge is increasing. And then that starts over when I once again go back to the s orbital. If we're looking for the valence electrons, a secondary feature is that going down a column, the effective nuclear charge just increases slightly because the electrons are less and less effective shielding as we go down the column. That's a secondary effect, though. Here's some questions applying that. So for the first one, we're looking at valence electrons. I have two neutral atoms, and I also have an ion in there. So for each of them, I would write what the electron configuration is, figure out the number of protons that we have, and then consider for the electron that we're analyzing, how many shielding electrons do we have? The one that's a little trickier here would be for sodium plus. When we're sodium plus, 1s2, 2s2, 2p6. And so we're removing one of those 2p electrons. The electrons that are shielding that have a smaller principal quantum number would be those with n equals 1. So that's why for sodium plus, there are only 2 shielding electrons. So these would be my calculations. What I'm trying to illustrate within the second question, we're again looking at valence electrons. If we're trying to rank these, we can do a preliminary calculation. Things are looking good, but we have 2 that have an effective nuclear charge of +1. This is now the idea that when we're comparing hydrogen and lithium going down a column, the effective nuclear charge increases slightly. So that's how I would be placing these. Valence electron, once again, what I'm trying to illustrate here is we can, for something like bromine, we can do the same type of calculation. Bromine would have an argon core, 3d10, 4s2, 4p5. We can look to see that it's number 35, so it has 35 protons. The shielding electron for one of those 4p, we have the argon core, and then we have the 10 electrons coming with a smaller principal quantum number. So just like the other halogens, it ends up having an effective nuclear charge of +7. Here we're doing a comparison of the 2s electron, comparing that in sodium and in carbon. We can do the same kind of setup. We can look for the number of protons in each case. For a 2s electron, the only shielding electrons would be in the 1s. And that's true for both of them, so we can calculate the effective nuclear charge in both cases. My point here is you can calculate the effective nuclear charge for any electron. We need to be careful to see which one's being described. Within our last one, we're doing a comparison of the 2p electrons and the valence electrons. I'm finding both of those, and once again, we can do our analysis for any electron. I think the effective nuclear charge is greater for the 2p in xenon because it has more protons. If I'm looking at the valence, I have one that is a noble gas, one's a halogen. The effective nuclear charge has increased as I move all the way to reach the noble gas. So that would also be larger for xenon. When I'm looking at the size, I'm thinking that I have two different trends. As I move from the top to the bottom, the principal quantum number gets bigger. So the shells are getting further away from the nucleus. When I move left to right, I think there's a contraction as the effective nuclear charge increases. I'm also thinking how cations are smaller than the corresponding neutral atom. Anions become larger, and we oftentimes have isoelectronic comparisons. Then the different questions, its first one's an isoelectronic one. All of the examples here have 10 electrons. So I'm going to look to the number of protons. More protons makes it a smaller size. Within the next ranking, I'm looking at a few different features. I know that magnesium is smaller than calcium. I'm looking at that just based on the same column that they're in. I know that a magnesium ion is smaller than magnesium because cations are smaller. How about calcium 2 plus? Well, that would be isoelectronic with argon. That would be smaller than argon. It's smaller than magnesium. So I'm using that information to put together my overall ranking. It's not just looking at one feature, it's looking at several comparisons. Same thing here where I'm looking at several comparisons. Oxygen is smaller than nitrogen as I'm moving left to right. I'm also thinking how anions are larger. So I know that both the nitride, nitrogen 3 minus, and oxide, oxygen 2 minus, are both larger than the corresponding neutral atoms. They're isoelectronic with each other, and because oxygen has more protons, it's smaller. So I'm looking at those features, bringing it together to get my overall ranking. Then this last set, I know that I initially have hydrogen, helium is smaller than that, and then lithium becomes larger once again because now I'm in a larger principal quantum number. So I could take an initial stab with those neutral ones. How about lithium as a cation? It has 3 protons and only 2 electrons. Helium had 2 protons and 2 electrons, so this would be even smaller than that. That would be my comparison. When I'm thinking about electron configuration of ions, to add an electron to make an anion, we're adding it to the next available spot when we're going with our building up principle. For cations, this is the one we need to be careful of. We always remove from the higher energy level based on the principal quantum number. We have to be especially careful with transition metals on that. And also be aware that the initial electron configuration might be one of the ones that we called anomalous. Several different questions pertaining to that. If we're looking here at a fluoride anion, it was 1s2, 2s2, 2p5 to make it an anion. It becomes 2p6. We no longer have any unpaired electrons. How about zinc 2 plus? With zinc 2 plus, I'm starting with the initial electron configuration. When it becomes 2 plus, I'm removing from the 4s, not from the 3d. I'm removing from the higher principal quantum number. So zinc 2 plus would be argon, and then 3d10, 10 electrons being found in the d orbitals. How about for the chromium 3 plus? That one begins with an anomalous electron configuration. When we remove 3 electrons, I would remove 1 from the 4s and then 2 from the 3d, so it ends up being argon 3d3. Key thing to look for, be careful with, is our treatment of cations. Ionization energy it requires to remove an electron from its gaseous state. We can remove 1 electron, 2 electrons, so we can have successive ionization energies. They're always endothermic. A smaller size corresponds to a higher ionization energy. And we had a few different exceptions that we noted along the way. Nitrogen and oxygen was a prime example. When we look at data for successive ionization, we see that it always increases to remove subsequent electrons, and we have a large disproportionate increase when we're removing one that's in a smaller principal quantum number closer to the nucleus. A couple different questions. Select the third ionization energy of boron. So I'm looking for removing the third electron to make it boron 3 plus, and I'm making sure they're in the gaseous state. In terms of successive ionization energy for an alkaline earth, I think I could remove 1 electron. It would take more energy to remove the second, but to remove the third, it's going to be much more difficult. I think that's the best description here. I could remove one, the second one's higher, the third's much higher. C is pretty close, but it has the first and the second on exactly the same energy level, same amount of energy, and I want to see that little increase instead. Looking at the ionization energy, now the second ionization energy, I'm thinking smaller size leads to a higher ionization energy. I have examples here where n equals 2 or n equals 3. It's going to be smaller in the n equals 2 shell. And in my comparison there, I'm choosing the one that has the most protons. I think F plus would be the smallest, so it had the largest second ionization energy. I want to be careful to see what electron I'm really talking about within my comparison here. How about within the next set? It's again looking at the second ionization energy. I'm not going to choose something that was like argon, that was n equals 3. I'm instead going to be looking at an n equals 2. When I take sodium plus, that's now isoelectronic with neon. How about neon plus? Okay, that's now isoelectronic with fluorine. In both of the cases, if we're doing a size comparison, I know that I'm removing an electron from n equals 2. We can calculate the effective nuclear charge. Sodium plus is plus 9. Neon is plus 8. I think the sodium plus would be smaller and therefore have a larger ionization energy. Adding electrons, that's electron affinity. A negative value indicating it is exothermic is favorable, but we have examples where it's a positive value and it's unfavorable. Things that contribute to it being favorable and exothermic, when we add the electron, we would like it close to the nucleus and experience a large effective nuclear charge. What would reduce the attraction it experiences would be pairing a negative electron with another negative electron in the same orbital. Those competing factors makes the trends here not as clear as what we saw with the ionization energy. If we look at some questions, first one would just be about the definition. I'm thinking about adding an electron to the anion in its gaseous state because it says the second electron affinity. I'm sure that's going to be very unfavorable. It's unfavorable, it's exothermic to add a negative electron to any anion, so to add a second one, that would be very unfavorable. But that would be the definition for it, what I list there. Which elements have a large exothermic electron affinity? There are examples of that. And also large exothermic ionization energy. There's no combination that fits both of those because all of my ionization energies are always endothermic. Factors that lead to an exothermic electron affinity. If we're adding it to a shell where it's going to experience a large effective nuclear charge, that would contribute and make it exothermic. The other factors that are being listed there, those are not going to make it exothermic. And then finally, which of these has the most exothermic, the most favorable electron affinity? I think it's adding an electron here to my halogen fluorine. The shell that it's being added to experiences a large effective nuclear charge. How about the oxygen minus anion? It's always unfavorable to add a negative electron to something that's already negative, like the oxygen minus anion. So that would not be an exothermic addition.